Okay, we're continuing to look at coordinates in space. So in other words, three-dimensional coordinates. And we have our traditional x, y, z, which are called rectangular coordinates. We have cylindrical coordinates, where x and y are basically converted to our traditional polar, and then z remains z. And before I even talk about this third case, let me just remind you that it is extremely useful to have this top view where we still look at our traditional two-dimensional graph paper, because if there is a point here, this gives us the radius in 2 dimensions, and our value of theta is here, because we're going to need some of this information to upgrade our three-dimensional coordinates. And this upgrade is called spherical coordinates. And you know how upgrades work. It might actually do more things, but it feels like it's a little bit more effort to get there to make it happen. Sometimes it's a lot harder. Spherical coordinates, I don't know if it'll be hard, but it is definitely different if you've never seen them before. Let me just tell you what the coordinates are. From our Greek alphabet, we have a letter that looks a lot like the letter P when I write it down. This is the letter rho. We have theta. That's the same theta. These are the same theta. Okay? These are identical to each other. That's this theta here, in case you missed it. And we have another angle, and it is spelled P-H-I, and it is either pronounced phi or it's pronounced phi. You know, it sounds like in the English language, phi or phi, depending on other letters in the traditional Greek alphabet. I'm going to usually call this phi because that's what most of my college instructors called it that used it. But again, this is one of those where tomato, the pronunciation may be different in different parts of the region. So rho, theta, and phi. Now let me show you how these three work, but before I do that little introduction visually, my students have access to a little formula sheet, but this formula sheet is nothing more than conversion formulas taken out of any multivariable calculus textbook or any source that talks about spherical conversion formulas online. I'm just going to put this up here really quickly so people can get a glimpse of it. Don't panic over this information in the bottom. This is for our last, near the end of the course, our last chapter plus. But I don't need you to worry about memorizing these formulas now. What I do need you to understand is, for this time being at least, what is the purpose or the meaning of these three numbers, and how do they find a point in space? Okay, and in case you missed the last segment, spherical coordinates is really good for talking about spheres. Orbits of electrons around this nucleus of an atom, satellites around a planet. Spherical coordinates are quite convenient for that. So we're going to switch modes of instruction here for just a moment, and let's use a visual aid to better determine how rho and theta and phi locate a particular point in space or 3 dimensions. So I've got here a little applet from website Math Insight, And thank you much to their offering up their applet to others to use. They have many other tools. Let's do this little rotation here. So there's a point here, and what I'm going to do first is focus on the theta. Remember, theta is if you were viewing from the top view down to the XY plane. Now you'd see a circle, and let's see if I can recover here. And theta rotates from the x-axis towards the y-axis all the way around, sort of like sitting in a swivel chair or an office chair. You could spin around, you can look different places. Theta is just that direction you're spinning. Okay, so that would be an XY plane measurement. So there would be pi over 2, and there would be pi, and there's 3 pi over 2, and there's 2 pi. We may occasionally go a little bit before 0 and a little bit after 2 pi, but the majority of our measurements, theta will be from 0 to 2 pi. Now rho is the radius from the origin. It's not a two-dimensional radius, it's wherever the point is anywhere in space, how far is it from the origin. So the way this picture looks, if the radius is smaller, if the radius is bigger, you can sort of see how that looks here. Let's move a point over here somewhere. If the point is closer to the origin or farther from the origin, so theta aims you over there, and rho is how far you're going to go. But that doesn't help you get things into space. Let's go down a little bit here. So here's the angle phi. I'm just going to mess around with it a little bit. Phi is 0, phi is pi over 2, phi is pi over 2, back to 0 again. Let's spin theta around a little bit. Whoa, where'd it go? Oh, phi is pi over 2, phi is pi. And let me just rotate this a little bit further. Phi is pi over 2, phi is pi. And I hope you can see that phi is measuring from the z-axis downwards, and it's the positive z-axis downwards. And all the way till you get to phi is pi, or 180 degrees, and you'll never go more than 180 degrees. It is always 0 to pi, because if you want to locate a point somewhere behind, you rotate theta and you face your chair that direction, and then this angle will always be from 0 to pi. And again, we can rotate this angle somewhere else. Phi goes from 0 to phi goes to pi. So if phi is 0, you're on the z-axis somewhere, positive side. And if phi is pi, you're on the negative side. And we can make the point closer or otherwise with the radius. So here's a smaller radius and here's a bigger radius, but it's measured from the point to the origin. It's not in 2 dimensions. Alright. Now, in our segments coming up, we will be looking at some numerical examples, but this applet is really handy for just messing around and trying to get the feel for how those work. Until next time.